Hello everyone, and welcome back to Mitchell's Physics Review. Today we will be working on magnetic force. Let's take a look at our problem. Consider the mass spectrometer shown schematically in the figure below. The magnitude of the electric field between the plates of the velocity selector is 2 times 10 to the third volts per meters. And the magnetic field in both the velocity selector and the deflection chamber has a magnitude of 0.03 teslas. Calculate the radius of the path for a singly charged ion having a mass of m equals 1.88 times 10 to the negative 26 kilograms. First, let's start by taking a look at our givens. E is equal to 2 times 10 to the third volts per meter, and the magnetic field B is equal to 0.03 teslas. M is equal to 1.88 times 10 to the negative 26 kilograms. It's also notable that it is a singly charged ion, meaning it will just have the elementary charge of a positive charge. Now, let's set up an equation. At first glance, this can look very tricky, especially because of the picture, the electric field, the magnetic field, the plates. But in the end, we know there's a force acting on the charge and that it's moving. So a safe bet would to start with and try first F equals ma. So for our equation here, we're going to start with the magnetic force equals mass times acceleration. We want it as it's going around the circular path, so we'll replace v squared over r for centripetal acceleration in our equation, and qv times b for the magnetic force. From there, we can then write the equation to solve for r, which is r equals mass times velocity over the charge times the magnetic field. If you haven't noticed, we've been given most of these variables. We've been given the mass, we've been given the charge, and we've been given the field. All that's left is to figure out the velocity. So now, to solve for the velocity, we're going to need to take a look at forces. Let's start by determining the direction of the magnetic force. We can do this through the right-hand rule. First, we're given that the magnetic field is into the page, so take your middle finger and point it towards the screen. Then we're given that velocity is pointing upwards, so we take our pointer finger and point it in the direction of velocity. As a result, our thumb then points towards the left, giving us the direction of the magnetic force. Now, we can add that on to our free body force diagram. Here's our positive charge and our magnetic force pointing to the left. You might be wondering, though, how I got this electrical force. So we figured that out through our picture. Remember, we have a positive charge in between two parallel plates, one positively charged and one negatively charged. If we have a positive charge and a positive plate to the left, we know that positive charges repulse, so there will be a force in the opposite direction to the right. Since we have a negative plate on the right, we know that a positive and negative will attract, meaning another force to the right. So our overall electrical force should be pointing towards the right. We can then set up the equation FB is equal to FE. From there, we can replace with QV times B equals EQ. As you notice, the charge drops out, and we're left with velocity equals to the electric field over the magnetic field. So, let's solve for our velocity now using the equation we just found through forces. We can plug in the given number for the electric field and the given number for the magnetic field, and in this case, I got the velocity to be 6.67 times 10 to the fourth meters per second. Now that we know the velocity, the charge, the mass and the magnetic field we can substitute in to solve for the radius. So plug in all the given numbers for those 4 quantities, plug into your calculator, and you should get r equals 0.26 meters. Overall, the hardest part of this problem for me was seeing how to get the velocity. We've been working in electricity so much and magnetism, it was easy to forget about simple free body force diagrams, which we drew all the time back in mechanics. So for me, I learned a lot about not just learning new stuff, but keep putting into use what we've learned before. This problem's helped me grow a lot. I hope it helped you a lot too. Thank you.